Hello viewers, welcome to my channel IITJ Olympiads and AP Physics with Ambarish, and today I brought one of the most requested topic in physics. This is one of the most dreaded topics also, and not just for students. As a teacher also, I know that when I started teaching transistors it was a nightmare because I could not understand a thing out of NCERT, and that's why I decided to do a video in great detail. In fact, I was just planning to do a problem video, but many students they wanted a detailed theory. So in this video, stay tuned till end. I'll give you all the required theory to the best of my understanding. I'll be solving a circuit, and then I'll be teaching you about the characteristics and why things happen in a transistor and how they happen. So a lot of things to discuss and a lot to learn, so please stay tuned till end to understand everything about transistors, especially in the common emitter mode. Okay, so without much ado, now let me get into the problem that I intended to do in this video. First I'll teach you how to do that problem, and then we'll see why things are the way they are. Okay, so let's have a look at the problem. Okay, so here is a circuit. Okay, so you can see this is a 5 kilo ohm resistor, then this is a 6 kilo ohm resistor, this is a 2 kilo ohm resistor, this is a 400 ohm resistor, and there is a transistor, and then this is a collector biasing battery, and this is the base biasing battery. So this is the circuit, and what is our aim? Our aim is to find for the transistor circuit shown in the figure, find IB, that is the base current. Okay, so this current I need to find out, this IB, and VCE I need to find out, that is the voltage between this point and this point. This voltage is VCE, and V0 is the voltage between the ground and this point. So this is your V0, this is your VCE between these points, and what's given is beta of the transistor is given as 200, and base emitter voltage is given as 0.7 volt. Okay, so don't worry, this might look a complicated problem to you, but we'll do all the theory that is required. And first I'll divide the solution into two parts. Okay, I'll divide this video into two parts. So two important things are what happens and why does it happen. Okay, so these are the two parts, and I've deliberately divided it into these two parts so that you get rid of the fear of transistors. So once you know how to solve this circuit, then we'll see that why that technique works. So once you are able to solve the problems, you get some confidence to and encouragement to study things in further detail. So first we learn how we do the problems, what exactly is happening, and then later part we'll be discussing the physics of it. Okay, so what happens when a transistor is in active region? This is a jargon for you. What do I mean by active region? See, this base voltage, when across this base emitter voltage, the biasing voltage is more than 0.7 volt, and the base collector battery is voltage is sufficiently large. That is, this battery is sufficiently large. We call that this transistor is in active state. Okay, so what happens in a transistor? Typically you see there is emitter, then there is base, and then there is collector. So emitter, base, and collector. Typically emitter is heavily doped, base is very lightly doped, and collector is moderately doped. So what happens? Emitter emits electrons, and this base region is very, very thin, and most of the electrons they'll pass into the collector region. Only very few electrons they will combine in the with the holes in the base. Okay, unless there is some kind of blockage in front. So that's what. Okay, so when the transistor is in the active region, this is the region where all the circuits are solved mostly. So what are the other regions? We'll see in detail. Okay, so following things happen. The transistor acts like a current splitter bearing constant ratio beta is IC by IB. So just for imagination, you can think of a T joint in a water flow. Okay, so let's say I have a pipe and you have a T joint over here, and water is flowing from here. So you know that some water will flow into the T joint, and some water will go in the forward direction. And the amount that goes in the forward direction, the amount that goes in the T junction, this will have some constant ratio depending on, in this case, maybe the diameters of the pipes, etc. So this ratio will be constant unless you put an obstruction over here and or you put an extra pump over here or some strange kind of things you start doing. Normally water will bear a constant ratio, the flow ratio will be constant. And similarly, if you talk in terms of the transistor jargon, so let's say emitter current is there, then part of it will go into the base and the other part will go into the collector. How that happens, we'll wait for a while. Okay. For now this is sufficient for understanding how to solve the circuits. Okay. And the base emitter junction behaves like a reverse biased battery, reverse battery of 0.7 volts. So, and these two facts, that is here you can think of that here in the base emitter junction there is some kind of reverse pumping mechanism of 0.7 volts. So but still the water can flow even if there is some reverse kind of pumping arrangement. Okay. Again, physics of it I am not discussing right now. After you are able to do the problem, after you are able to solve the circuit, then we will see the physics of it. So facts 1 and 2 are sufficient to solve just about every transistor circuit. And now I am going to discuss this in a lot more detail. Okay. So facts 1 and 2 enable us to make the following DC equivalent model of a silicon transistor. So what is the fact 1? That it is transistor is a current splitter. So there is a constant ratio between the collector current and the base current, and base emitter junction behaves like a battery of 0.7 volts. Okay. So so this is my transistor, let us say. So here there is, you can imagine that here base emitter junction, you can imagine that there is a battery of 0.7 volts against the emitter current. So this arrow represents the direction of emitter current and there is a reverse battery of 0.7 volts. Why that is there, I have not yet claimed that I have told it. I'll tell it later on. Okay, when we discuss the why of things. Right now we are discussing just the how of things. Okay. So whatever is the current here, base current, the collector current is going to be beta times that. Okay. So this transistor can be replaced equivalently by this DC equivalent. Okay. So here is IB and this is IC, which is nothing but beta times IB, and there is a battery VBE. So I hope this DC equivalent is clear. Once this is clear, now the transistor becomes our friend and we can very easily solve the circuits. So let's see how to solve the circuits. I'll take up a sample problem, simple illustration, and then I'll go to the more complicated illustration that I gave in the challenge video. Okay. So here is the circuit. This battery I have made for convenience. Okay. So find IB, IC and V0 in the transistor circuit of figure 3.41. So whatever I have written in this blue things, this is not given in the question. This pink things are not given in the question. Question only has this green resistors and these blue connectors, bluish, I don't know what color. And this I put 0.7 volt as per my DC modeling. Okay. So against the emitter current you put a 0.7 volt. Okay. And if this current is IB, then this current is beta times IB. Okay. Now we can easily apply, now it's just like a current electricity circuit, we can apply the standard Kirchhoff's voltage law, current junction laws. So now this loop I am calling as input loop and I am applying Kirchhoff's voltage law to this input loop. Okay. So what is the potential drop? So 20 kilo ohm voltage and 20 kilo ohm resistor and IB is the current. So 20 kilo ohm into IB, this is the drop across this, and then there is a drop of 0.7, so plus 0.7, and then you come to this battery, this is 0 minus 4 volt is equal to 0. So I hope you understood how I made this equation A. So this IR, this battery, and then coming to this battery, this is equal to 0. Okay. And now using this you can easily solve this equation. The only unknown in this is the base current IB, and if you solve, that comes out to be 165 microampere. Okay. So once you know the base current, now you can easily find the this one beta times IB. So beta is given as 50 in the problem, beta is 50, so you just multiply this by 50 and this is your 8.25 milliampere. Okay. So I have found base current, I have found the collector current, and now I also want to find out V0. So what I can do, I can travel from P to Q to S to T. So when I travel from P to T in this way, I keep on adding all the potential drop, and that gives me the total potential drop, which is V0. Okay. So let's do that. Now to find V0, we traverse along the path PQST, and when I'm doing that, so I'm traveling against the current here. So potential drop is minus IC into 100. This is 100 ohm. So minus IC because against the current I'm moving, and then there is plus 6, so plus 6, and now we have reached to point T, and this should be equal to V0, summation of all the potential drops from P to T. Okay, and IC I've already found out, so I just substitute the value of IC in here and then solve for V0, and if I do that, V0 comes out to be 5.175 volts. So I hope you understood this illustration. It's very important to understand this illustration. If you want, you can try to work out this yourself, and this illustration will give you a lot of confidence in solving transistor circuits. Okay, and now I'm going to do a little more complicated circuit. I hope you understood this. If you want, you can rewind this and try out the working of this problem on your own. Okay, now I'll complicate things a little more so that you get even more confidence in solving the circuits. So now let me take the problem that I posted on the community page, that is the challenge problem that I gave yesterday. So in this one, a little more complicated. So here once again, the things in red are not part of the problems. I have mentioned them on for the purpose of solving, but yes, the green, the resistors are given, all the circuit elements are given. Again, this 0.7 volt I have put here for the modeling that I explained. How do we model the DC equivalent of transistor? Okay, and here the current is IB, so here the current is beta times IB in the collector. Okay, so beta is given as 200. This was given in the problem, beta 200. Other things I have just marked for purpose of illustrating. Okay, and what do we have to find out? Once again, we have to suppose find out IB, IC, and this V0 and VCE. That's what was to be found in the original problem. 4 quantities: IB, VCE, V0, and IC. Okay, and beta is given as 200. Okay, so now I can do it in two ways. So the easy to understand method would be, I consider apply KVL to this loop. I have called this as loop A. So I apply KVL to loop A, then I apply KVL to loop B, and then solving these two loops, I will get the value of IB, and I've assumed this current as X. So IB and X I'll be able to solve by applying KVL to these two loops, and once I know IB, then I'll be able to find out IC and other things. Or otherwise, if you want to save some time, you can play a little gymnastics here. You can Thévenize this. Okay, so you can see the circled portion has got only resistors and battery, so you can just make it a single battery and a single series resistor. If you want, you can do that. That's perfectly valid way of doing it. I like to do it that way, but for the purpose of illustration, I'm avoiding the Thevenin approach. Okay, so I'll do it in the classic way that we do the applying loop law. So just for the didactics, okay, demonstration. Okay, so now so loop A I'm trying to apply. So this current is IB and this is X, so this becomes IB plus X. The current through 6 kilo ohm becomes IB plus X. Okay, so in this loop, IB plus X into 6 kilo ohm, so that's what I've written, IB plus X into 6 kilo ohm. Then you come to 2 kilo ohm, so 2 kilo ohm into X, so that's what I've written, 2 kilo ohm into X. And then you come to this battery, this is minus 3 equal to 0. So summation of all the potential drops is 0. So this is one equation at IB and X. Now for loop B, if you see, you go from here IB and you cross this reverse battery, that is 0.7 volts. So that's what I've written, 0.7 volts over here. And once you cross this battery, then here again the current must be IC plus IB. See, IB is coming from here and IC is coming from here. So emitter current is nothing but summation of these two currents by junction law, you can see. So whatever current is entering the transistor, same current is leaving the transistor through the emitter. Okay, so what is happening, actually, you know that current is against the flow of electrons. So actually what is happening, the emitter is emitting electrons into this base, and then many of them are going into collector and some of them are going here, but the conventional current is shown opposite to the flow of electrons. Okay, so now I have this equation, the second equation also we can make. So this is IC plus IB. Okay, and IC is nothing but beta times IB, right? So I have directly written, instead of IC plus IB, I have written IB plus beta IB into 400. Okay, so this one is beta IB plus beta IB into 400 ohm, and then you go back here and this you are going against the flow of current, so minus X into 2 kilo ohm for this one. Okay, and this is equal to 0 again. Okay, so now in these two equations, if you see, I have two unknowns. One is the X, other is IB, and I can easily solve this simultaneous equation. So if I solve, I get IB as 0.61 microampere. Okay, this one is 0.61 microampere, and X comes out to be 0.3 milliampere. Okay, so this current is 0.3 milliampere. And now once I know IB and X, I can easily find the value of V0. So V0 is what you see. V0 is the drop across this 400 ohm resistor. So what is the current? IC plus IB and into 400. Okay. So V0 is IB and IC is beta IB. So IB plus beta IB into 400. So beta is 200. So this becomes 201 IB. So 201 IB, and so that is 201 into 0.61 microampere into 400. If you solve that, that comes out to be 49.08 millivolt. So I have also found the value of V0. Now of course IC is 200 times IB. So IC I have also readily found. Now I want to find out VCE. So VCE is what? See, VCE is the potential drop from this point to this point. So what I can do, I can travel from P to Q to S to T and back to this place. Or otherwise I can say that whatever is the drop from P to Q to S to T, this drop is equal to VCE plus V0. Okay, and V0 I've already found out. So I'll take this drop from P to T and then subtract V0 to get the value of VCE. So that's what I've written. Let's see. So so minus 5 kilo ohm into 200 into 0.6 microampere. So what does this represent? See, this 5 kilo ohm resistor. Okay, and the current is 200 times 0.61 microampere for IB. Okay, so and you're going against the current, therefore a minus sign. So that's what I've written. See, minus 5 kilo ohm into 200 into 0.61, that was the base current. Okay, so 200 times base current is the collector current. Then you hit this 9 volt battery, so you write plus 9. Okay, so that's what I've written. So plus 9, and this should be equal to VCE plus 49 millivolt that I've already found here. Okay, or rather to be precise, 49.08 millivolt. Okay, so this plus this is same as this total drop. That's what I've done, and solving this I get VCE as 8.34 volts. So VCE is also found. Okay, so this was how to solve the circuits. Okay, so I'm sure you understood how you solve the circuits, and now comes the important part, that why this method works and what exactly is happening, why this 0.7 volt battery, why it's not changing, and all those things, and why this transistor is acting like a current splitter and all. So those things we'll see in a lot more detail now. Okay, so why does the DC model work? So now the explanation of VBE is equal to 0.7 volt, that lies in the diode characteristics. Why? Because the base emitter junction is somewhat like a forward bias diode. You see, here you have an emitter and then you have a base, and this is N and this is P. So this is somewhat like diode like kind of junction. Okay, and it does bear some similarity to the diodes. Okay, so diode characteristics, base emitter junction is somewhat like a forward bias diode. Out of all the applied voltage, 0.7 volt is consumed in bridging the depletion layer. So if you recall from your knowledge on diodes, that initially depletion layer is large, and when you bias the diode, so until certain voltage is applied, the diode doesn't get properly forward biased. The depletion layer is still there, and the depletion layer gets bridged around 0.7 volts, right? And then once the depletion layer is bridged, the crystal's resistance goes down, because until the depletion layer is bridged, practically the crystal has got infinite resistance, because there are no charge carriers in the depletion layers, right? Practically there are no charge carriers, except for some minority flow. And once the depletion layer is bridged properly, then the current starts flowing. So whatever voltage you apply, let us say you apply 3 volts, out of that 0.7 volts around goes in the bridging of depletion layer, and then you have so what is the diode characteristics? So here you can see this is the forward bias diode characteristics. Here I have shown. Okay, so forward bias can be approximately simplified by the blue line. So actual curve is this, the black one, but if you draw a tangent to this and you can approximate it as a flat horizontal line up till 0.7 volt, and then it's like a straight line after 0.7 volt. So nearly ohmic response, you can see that voltage and current are nearly proportional after that. Not proportional, but I can say that it has got some kind of a straight line behavior. So this leads to a following equivalent DC model of diode. You see, so you put a battery, reverse battery of 0.7 volts, and then you put a ohmic resistor, and then what is the current through this? You know that straight line behavior can be easily modeled using a battery and a ohmic resistor. So if you apply, suppose let us say you apply 3 volts over here. So out of 3 volts, you know that you have to subtract this 0.7 volt. So the current will be 3 volt minus 0.7 volt, that is 2.3 volt, divided by this 10 ohm. So basically this model, this characteristic curve is essentially a combination of a battery, reverse battery of 0.7 volt followed by an ohmic resistor. So this is very important. Okay, so this is the DC model of a diode. Okay, the actual diode approximate model. Instead of taking the curve, we suppose we are operating somewhere over this point, so then this is a very good approximation of the diode that we can use. Okay, so now whatever voltage is applied across the diode, the current is almost, suppose V is the voltage, then the current will be V minus 0.7 divided by the dynamic resistance of this diode, which is 10 ohm. Okay, now let's try to understand the common emitter characteristics of a transistor. So this is the figure of a transistor in NPN transistor in the the common emitter mode. So emitter is connected to this battery, this is base biasing battery, and the other terminal is connected to the collector biasing battery. Okay, so now what is happening here? So emitter is ejecting lot of electrons into the base because of this battery. You see, in semiconductors, it's often convenient to think of battery as not just emitting some positive charge. Think that battery is emitting holes from its negative terminal, and it's emitting so it is emitting electrons from its negative terminal, and it's emitting holes from its positive terminal. So simultaneously it is emitting both. You can imagine battery to be like that. Often that visualization is helpful. So what's happening from the negative terminal of the battery? Electrons are being ejected into the emitter. Now what's happening? So base is very, very thin, unlike the diode. Here the base is a very, very thin layer, and it is very lightly doped. So whatever electrons are ejected into the base, so most of them will cross over to the collector side. Why? Because the base is very, very thin, and the second thing is that base has got very light doping. So very few holes are available in the base, so electrons cannot combine with the holes in the base. Most of the electrons, they will go into the collector, and that's why it is shown that base current is very, very small and collector current is almost same as the emitter current. So actually the electron flow is like this, and this arrow is for the conventional current. So conventional current is in the downward direction against the flow of electrons. So this plus this, they join together to form the emitter current. So that's simply junction law. Base current and collector current together should be equal to the emitter current. Okay, and now what is the characteristics, input characteristic curve? So input characteristic curve is between the base emitter applied voltage versus the base current. Okay, so you can see here until about 0, again once again if you draw the tangent over here, then that cuts it somewhere around 0.7 volts. Okay, if you are operating somewhere over here. So what we are doing, we are changing the value of VCE, collector emitter battery values we are changing, and we are seeing how the base current varies with the base emitter applied voltage. Now what happens, you can see whether VCE is 1 volt or 10 volts or 20 volts, this curve is shifting very little based on VCE. Now what happens? So electron has been ejected into the base, but the collector is a region of high resistance, and it wants the electrons that have reached the collector, they are asking somebody should be there to welcome us, right? That's why this is the reverse bias battery which is there to welcome the electrons. So whatever electrons are passed into the collector, if somebody is there to welcome, they'll then go over to the other side. If there are too many people to welcome, it doesn't matter. I mean, the number of people reaching here will be only dependent on how many people have crossed. So even if there is one person, you're welcoming them just by one person has come to receive them, so 1 volt is there, still almost the current is same. And if you welcome them using 10 volts, still the current is almost same, because whatever is the number of electrons that's crossed into collector, more than that cannot go here. Okay, So it's like that. So there's not much of a difference when you change this VCE. Actually here is VCE or VCC is same thing, because here I have not shown any resistance. So VCE or VCC is almost the same thing here. Okay. So let's say 1000 people have crossed this base, and then there's one person to receive them, so almost 1000 or maybe 999 feel motivated enough to go. But if you have 1000 people calling it, then maybe, or maybe 10 people coming to receive them, a little more number of electrons will feel motivated to go there, but it doesn't make a lot of difference. Okay. So so this battery doesn't make, but definitely there should be some biasing, but otherwise electron, if you do not welcome these electrons, they have no motivation to cross this region of very high resistance. Okay. So but if you apply very high voltage, if you welcome them with lot of garlands and pomp and show, and you bring brass band and all, that doesn't make much of a difference to the number of people crossing here. Okay. But yes, somebody should be there to receive them. Okay. So that explains this characteristic curve for the input characteristic, that is this base biasing battery. This should be more than 0.7 volts, that's all. And once it is more than 0.7 volts, so base current varies as shown here. Okay. Okay. So input characteristics are similar to forward bias diode. Note that VCE does not make a significant difference to IB. All characteristic curves are close together. Okay. So this doesn't make much of a difference to this. Okay. We can also plot emitter current versus base emitter graphs, which are successfully approximated as follows. So you realize here base current is in microamperes, because most of electrons will actually cross into the collector. That's why this is in microampere, but the collector current is going to be in milliampere, which will be almost equal to the emitter current. Okay. And emitter current is also going to be in milliampere. So I can also plot the emitter current versus the base emitter voltage. This is supposed to be VBE. Okay. Emitter current versus VBE I can plot, and this is the actual curve, actual diode kind of behavior. And this is the first approximation where I can make it like an ohmic resistor and then followed by a 0.7 volt battery. This is the first approximation, but this line is since very almost vertical line, and if I'm operating somewhere over here, I can as well approximate this as a vertical kind of line. So this is the approximation that we are using for DC model of transistor, right? So so that's why we are taking base emitter voltage standard value as 0.7 volt. Sometimes it is given 0.6 or even 0.65, but most of the good textbooks, they just take it as 0.7 volts. Okay. So this is where that 0.7 volt battery is coming from, that diode kind of behavior of the base emitter junction, right? Note that VB is not literally constant, but almost workably constant. Okay. So this is not constant actually. You see voltage is increasing a little bit, but if you are working somewhere over here around these voltages, you can assume this is 0.7 volt for modeling the behavior. Okay. So it is workably constant, almost workably constant. For instance, if we are operating the transistor near the red cross mark points, so these points we are operating. Okay, similarly we can also plot this graph between base current and VBE. So base current versus VBE can be approximated like this. See, this is the actual curve that I showed, and this again I can model it as a vertical line that I am showing later on. Okay, so this is the base current versus the base emitter voltage, and you can see we are operating near this point, and 0.7 volt is almost constant, you can see, and base current can change at the same voltage, nearly the same voltage. The graph is almost vertical. Okay. So this, I hope that you understood why VBE was assumed to be constant and VBE was taken as 0.7 volt. Remember, in the first part I told you how things happen, and now I've told you why things happen. So I hope you understood that why we are taking VBE as 0.7 volt. So this is the workable approximation for the base emitter junction, right? Now let us try to understand the output characteristics. So what is the output characteristics for a common emitter configuration? Output characteristics is the collector current versus the collector emitter voltage. Okay, so this is C and this is E, so there will be some voltage between collector and emitter. Okay, and that will be nothing but, see, there is actually some resistance. In the earlier figure I did not show the resistance, but in practice there will be some resistance. Even if you do not attach an external resistor, there will be some small resistance. So what happens, like what is the potential drop across this? So this is VCC and suppose this is IC. So net drop between emitter and collector is VC minus IC RC, right? If this is RC, okay, that is the net drop, okay. And in this region there are, I mean, if you see the output characteristics, you can see different regions. So in here you can see this is being called as saturation region and this is being called as cutoff region. It's very important to understand what is saturation and what is cutoff. And of course this is where the area of interest is. Mostly we are operating the transistor in the active region. So let's try to understand all these terms. What is cutoff region, what is saturation region, and what is the active region. So what is the cutoff region? So when the applied voltage across the base emitter junction is less than 0.7 volt, the collector current is practically zero. Why is that? You remember that base emitter junction is somewhat like forward bias diode, and until you apply 0.7 volt, the diode is not properly forward biased, so there is no current, okay. You know that when diode is not properly forward biased, there is no current, right? So, and when no current means what? Emitter is not emitting anything into the base. When emitter is not emitting anything into the base, then how can collector have anything, right? Because collector only collects whatever is crossing the base into the collector, right? So when the applied voltage across the base emitter junction is less than 0.7 volt, the collector current is practically zero, okay. So this is where it is shown. So base current is also 0 microampere and the collector current is also 0 microampere, and therefore so whatever battery you are applying here, we see IC is 0, so there is no drop across this resistor. So whatever is this battery value, the same is VC. So that's what is shown in the cutoff region. In the cutoff region there is absolutely no current in the collector. I mean, I'm not talking about the minority carriers and the small little microampere currents, but practically there is no current in the collector, okay. Now what is the other region? This region is saturation region. So what is the meaning of saturation region? See what will happen if you so let's talk about saturation region. So see, VCE will be VCC minus ICRC. Let me show this to you in the circuit. You see here this is VCC and this is RC. So what is the drop from here to here? So minus ICRC and plus VCC. That's what I've written. VCE, that is the voltage between collector and emitter, is VCC minus ICRC. Now when VCC is sufficiently low, when this battery is sufficiently small, or IC is sufficiently large. So when VCC is sufficiently low or IC is sufficiently high, then VCE becomes 0. So this drop becomes nearly 0. And when that happens, that we are calling as saturation region, right? So this is the saturation region. Here what is happening? Either the applied collector emitter battery is very small or the current is very high. So VCE, so net voltage drop between C and E becomes 0. So that is the saturation region. So I hope you understood the cutoff and the saturation region. So very high collector current, that will lead to saturation, and zero collector current, that is the cutoff region. And when these two cases are not there, then rest of the region is the active region, right? So what is the active region? When base emitter junction biasing is sufficiently large, VCE is also sufficiently large, the collector current bears almost constant ratio to the base current. So in the active region, the collector current and the base current are in a constant ratio, and that's what we were using. So that we were calling that as the beta of the transistor, right? When the ratio is constant. So here is a better curve. You can see in this active region, if you see base current here is 20 microampere and the collector current is 4 microampere. So you can divide 4 milliampere by 20 microampere and you will get beta as 200. Similarly, 3 milliampere you divide by 15 microampere, or 2 milliampere you divide by 10 microampere, etc. So this ratio is called the beta. And you see when you are dividing the absolute current by the absolute current, what you get is what is known as the beta DC, okay. So here 4 milliampere is the absolute current and 20 microampere is also absolute current. So the ratio of these two is the beta DC. But you can also find out quantity called dynamic beta or AC beta, that is delta IC over delta IB. So that is called the beta dynamic. Okay, so beta DC, and both happen to be almost same in most of the transistors. Both happen to be nearly same. For example, here if you see, the change in base current is 20 microamperes minus 50 microampere, that is 5 microampere. And here if you see, this is 4 milliampere minus 3 milliampere. So 4 minus 3 becomes 1 milliampere, and this becomes 5 microampere. You take the ratio, so delta IC upon delta IB will also be coming to be 200. So generally beta DC and beta AC in the active region are nearly same. Okay, so so you can see in the active region, because the ratio of base current and collector current is constant, that's why we were taking collector current as simply beta times base current. Okay, so this, I hope you understood why in the active region the collector bears a constant ratio to the base current, collector current. Okay, so this is it. Okay, I deliberately chose this figure so that this concept is very clear. You can verify a similar kind of thing happening in this also, but the explanation would have been a little messy because these curves are not absolutely horizontal, and I'll have to read between the grid lines what is the current. But I hope you understood, and this is a better graph. I literally made them horizontal here. So I hope you understood what's happening, and beta base current and collector current are bearing a constant ratio here. So it's like pipe without any obstruction over here, and normal water is flowing. So some is going here and some is going there. But what happens when you start flooding it, then strange kind of things happen. Let us say here there is a limit, there is some kind of a valve you can see which doesn't allow too much water to flow. So some kind of things can happen there. Okay, but otherwise in the normal circumstances the two water flow ratios are constant. So that is collector to base current. So I hope you understood why in the active region collector current bears a constant ratio to the base current. Now the next thing is the transfer characteristics. So transfer characteristics is the graph between the input voltage and the output. This is the figure from NCERT that I have taken, this one. And here this is the input voltage, this VBB, this I am calling as the input voltage. This is a voltmeter to measure the input voltage, VBB. This is a variable battery over here, and here this I am calling as V output. Okay, again there is a biasing battery, is a variable battery. This I am calling as collector resistance, this I am calling as the base resistance. So these could be the external resistors that you have connected in the circuit. So what happens when you change the input voltage, the output voltage will also change. And now I am interested in finding out what is the behavior between the input voltage and the output voltage. Okay, so what is happening? Typically the output voltage, this biasing battery will be somewhere around 20 volt to 50 volt or something like that, order of 20 to 50 volts, while the input voltage, this will be order of 2 to 5 volts. This biasing battery will be typically 2 volt to 5 volt. Okay, can be little more here and there, but about 2 to 5 volts, and this is about 20 to 50 volts. Okay, could be more than that also. Okay, so output voltage is of the order of about 20 to 50 volts, while the input voltage is of the order of 2 to 5 volts typically. So this is going to have a very large slope. So let me explain this graph in more detail. What is happening when suppose input voltage is very small? So when the input voltage is very small, what will happen? The base emitter junction is not properly forward biased, and when the base emitter junction is not properly forward biased, there is practically no current. So emitter is not giving out any current, so therefore collector current is 0, and if the collector current is 0, there is absolutely no drop across this RC. So whatever is the value of VC, that you are getting as output. So you are getting the full value of VC. Why? Because the output voltage is actually VCC minus ICRC. So when IC is 0, then you are getting entire VCC as the output voltage. So what's happening? So when the input voltage is very small, the transistor is in the cutoff region. Okay, and you are getting a very high value of the output voltage, right? And similarly, what happens when the transistor is saturating? So when there's a very high current flowing through the collector because of because of high input voltage being high. So when you are giving it nice input voltage base emitter junction, then you know that the graph of the current is almost vertical, a little slant but almost vertical. So current increases a lot by just a little bit of increase of the input voltage, and when the current increases a lot, collector current increases a lot, what happens? Again, the output voltage is VCC minus ICRC, and when IC becomes very large, IC becomes very large, then VCC minus ICRC goes to 0. So that's what's happening. So when the input voltage becomes large enough, so then the transistor saturates and the output voltage goes to 0, which is VCC minus ICRC goes to 0. So this is the cutoff region and this is the saturation region. And you can see here the behavior is, for low input voltage you are getting high output voltage, and for high input voltage you are getting low output voltage. And this behavior is called the behavior of a NOT gate. When the input is high, you get a low output, and when the input is low, you get a high output. So when you are using the transistors, this region and this region, you call it as a switch or a NOT gate. So that's the working of a transistor as a switch or a NOT gate. So low input, high output, and high input gives you low output. Okay, so that's transistor as a NOT gate. And now in the active region, you see again output voltage is what? VCC minus ICRC. Okay, so what happens as you keep on increasing the input voltage, base current keeps on increasing. With even just very slight change in input voltage, base current increases drastically because of this kind of characteristics. Okay, or very, very steep characteristics. So input voltage changes a little and output the input current changes by a lot. And when the emitter current changes by a lot, collector current also changes by a lot, and therefore output voltage also starts changing very rapidly. So this graph has got a very steep kind of slope. So for very slight change, so this is of the order of 2 to 5 volts, and this change will be then order of 20 to 50 volts. So you can see small input changes in the input leads to large change in the output voltages, and this is the principle for the amplifier that we will see more mathematically in a little while. Okay, so that's what I have written. Output voltage is of the order of 20 to 50 volts, while the input voltage is of the order of 2 to 5 volts typically. Thus a large slope of the transfer curve causes the voltage amplification. So I hope you understood. This is a very, very steep curve. Okay, so this 2 volts and this is then 20 volts approximately. Okay, so causes a voltage amplification. So small change in input leads to a large change in the output voltage. Please remember there is a resistor over here, so don't think that this biasing battery is exactly VB, because VB is still around 0.7 volt, a little bit here and there. But if you keep on increasing voltage, this base current will keep on increasing, and there will be some drop across this RB also. Not entire drop is across base emitter junction. Base emitter junction is still 0.7 volts. Okay. Now we can talk about transistor as an amplifier. Okay. So this is the circuit for transistor as amplifier. Let's try to understand how it works. So input voltage is what? So this loop, if you consider, this drop is IBRB and there is 0.7 volt VBE. Okay, so input voltage is IBRB plus VBE. Okay, so what is the change in input voltage? See, change in VB is negligible. It is almost equal to 0.7 volt. So whatever is the change in this, we can say that is the change in the input voltage. Okay, IBRB is RB into delta IB. So if you take delta VI, this becomes delta of this term plus delta of this term, but delta of this term goes to 0, and delta of this term, since RB is constant, so this is RB into delta IB. So this is the change in input voltage, right? So what you will be doing practically what will happen is over and above this base biasing battery, let's say you want to amplify your voice signal. So you will start inputting, let's say you have a microphone, and you have the wires coming off the microphone. So you put one wire over here, one wire over here. So whatever is the voltage signal of the microphone, that gets superposed on the VBB, and this is small signals, they are getting superposed over VBB, and then they are getting amplified. Okay, so this variable battery is here it is shown, but this variable battery is effectively, this is a constant battery plus the voltage signals due to the microphones being superposed on this VBB. You can think of it like that when you are amplifying the sound signal coming from microphone. So this variable is basically you must have seen when you are doing MP3 recordings, you might have seen that there's some kind of this kind of graph is made in your MP3 players. Actually this represents the voltage signal or the current signal corresponding to whatever is the voice signal, and this signal is superposed on the biasing battery. Okay, and because there are small signals, small fluctuations in the input signal, it leads to large changes in the output signal. And what's happening, the output voltage, this is going into some kind of a speaker, okay, and since for small input changes from the microphone, there are large input changes, large output changes in the voltage that is going to the speaker, so that leads to the amplification of your signal, right? So change in input voltage is simply RB into delta IB. And what about the output voltage? So you see output voltage is VCC minus ICRC. So what is the change in output voltage? You see VCC is constant, but then this can be constant. I mean, NCERT shows a variable battery, but you can even keep it constant. And ICRC, this is going to change. So suppose you are keeping VCC at some value, some constant value, then what is the change in output voltage? So VCC change is 0, and then RC into delta IC is the change in the output voltage. In fact, there's a minus sign, right? Because there is a minus sign here, okay? So now what is the voltage amplification? So change in output voltage divided by change in input voltage, right? So I messed up here. This should have been change in output voltage, change in output voltage divided by change in input voltage, right? And this is then RC delta IC, see, minus RC delta IC divided by RB delta IB, okay? So this is called the dynamic voltage gain, okay? So beta, you can, if you want, you can write beta AC here, or dynamic, beta dynamic into RC upon RB. So this is your voltage gain. I hope you understood how the transistor acts like voltage amplifier, right? And of course current gain is delta IC upon delta IB, and then you also define something called power gain. Power gain is voltage gain multiplied by the current gain. So if you do that, so there's already one beta AC here, and you multiply it by another beta AC, so this becomes beta AC squared times RC by RB, okay? So for example, okay, so important thing to note here is that output voltage, if you see there's a minus sign over here, that means output voltage is pi out of phase with the input voltage. I mean, whatever are the changes happening in the input voltage, the output voltage changes are pi shifted and amplified, okay? So for example, suppose oh, I forgot to make the graph, but let me make it here right away. So suppose your input signal is like this, let us say input signal is something like this, let us say this is about 2 volt and minus 2 volt. So output signal will be what? Output signal may be something like inverted, and it will be going up and down, and this could be maybe 20 volts and minus 20 volts, okay, depending on what is the amplification that is achieved. So if it is amplification of 100 times, then it will become 200 and minus 200. So with beta of okay, so this is 200 and minus 200. This is the, so important thing to note here is the graph is inverted over here. So this is what is meant by pi shift, okay? Okay, so that's our theory for common emitter transistor circuit. I'll also try to cover common base circuit, although it's not mentioned explicitly in JEE syllabus and it's not given in NCERT. I'll do one more video to illustrate common base amplifier. I didn't want to make this video too long, it's already too long. But I tried to explain the transistors to the best of my capability, and I hope you understood, and this made things a lot more clear to you. And if you think that you benefited from this video, please do give it a thumbs up, and please share this video as much as possible with your friends through WhatsApp, Telegram, Discord, or whatever medium you might be using for networking with them. And most importantly, if you're not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to do a new video almost every day. And thanks a lot for watching this video, and I'll see you in the next one. And as always, God bless you all. Thank you.